Okay, guys, so now we're going to talk about how to approximate a system of equation using Taylor method of order 2. All right, and again, this can be extended to Taylor method of order 3, 4, 5, and so forth. You can kind of go crazy with this, but let's keep it simple. Let's keep it simple as far as we can. So, a system of equation, approximation. Of course, when we're talking about system of equations, we're talking about system of differential equations. Approximation. Okay. And we're going to look at the Taylor series, Taylor method of order 2. Order 2. And it looks like this. Very straightforward. Suppose I have, again, it's going to be x of n plus 1 equal to x of n, okay, plus h of xn prime plus h squared over 2 of xn double prime. And I just put the h's in front just to make it a little bit easier. And then we have y sub n plus 1 is equal to y sub n, just makes it a little bit nicer to look at, plus h y sub n prime plus h squared over 2 y sub n double prime. Okay. So this is our Taylor method of order 2 for a system of equations. This is just 2 equations system. But again, you can extend this equation system to 3 equations, 4 equations, 100 equations. It will work exactly the same way. Okay, so here we go. I want to find the Taylor method of order 2 for, and we're going to do the same one we did before. I have x prime equal t plus x squared minus y, y prime equals t squared minus x plus y squared. Okay. X of 0 is equal to 3, y sub 0 is equal to 2. Okay. I want to be able to approximate this particular differential equation system. And notice what we need for the Taylor method, right? I need to know what x and y prime are, which I've already been given. This is x and y prime. I also need to know x double prime and y double prime. So I need to figure out what is x double prime and y double prime. Let's find x double prime first. X double prime is equal to the derivative of x prime, right? So that's going to be the derivative x prime. Okay. Now, when we do this, this is going to be equal to the derivative of t, which is 1, plus, if you guys remember the chain rule, this is going to be 2x times x prime, right? That's how the chain rule works. The derivative of y is going to be y prime. Okay, and let's plug in what that's going to be equal to. We don't know what x is, but we know what x prime is. So we have 1 plus 2x times x prime, which is t plus x squared minus y, minus y prime, which is going to be t squared minus x plus y squared. Okay, that's what x double prime is equal to. If you were to work that out, at least this is what I have. When you were to, if you were to multiply that out, I get x double prime is equal to, actually I'll just keep it the way I have it. X double prime is equal to 1 plus 2x. We'll just leave it that way. We'll just leave it as it is. We'll box it that. It's good enough. I don't want to have to rewrite that again. I don't have enough space for that. So this is my x double prime. Okay. And let's do y double prime real quick. Y double prime is equal to, we want to take the derivative of y prime. So I get t squared minus x plus y squared prime. So when we work on this one, right, the derivative of t squared is 2t. Okay, derivative of t squared is 2t. The derivative of x is x prime. Okay. The derivative of y squared is going to be, by chain rule, 2y prime, because we're taking the derivative with respect to t. Okay. Y is a function of t. And let's just plug in. Let's see what we get. 2t, y double prime is equal to 2t, minus x prime, so the coordinate x prime is t, plus x squared minus y, plus 2y. We don't know what y is, but we know what y prime is. Y prime is t squared minus x plus y squared. Okay. So that is our y double prime. Let's box that one as well. See how nasty this is, right? Can you see? It's pretty nasty. Okay, pretty nasty. And let's do, last but not least, all right, let's combine it all together into this one monster equation. Can you guys see? Oh, this is gonna be horrible. I think I have enough space to put it here. So we have x and n, so Taylor series, let's combine everything together. Combining everything. All the equations. We have, for our Taylor method of order 2, we have x of n plus what? Is equal to x of n plus h times the quantity x of n, which is going to be t sub n, plus x sub n squared minus y sub n, okay, plus h squared over 2 times x of n double prime, which is this thing down here. So we get 1 plus 2 x of n times the quantity 2 times the quantity t sub n plus x of n squared minus y sub n minus t sub n squared minus x of n plus y sub n squared. I'm going to put brackets around that whole thing right there, because it's going to all be multiplied by h squared divided by 2. And then y sub n squared, so y sub n plus 1 is going to be similar. It's equal to y sub n plus h times, looking at this, the derivative of y, which is t sub n squared, minus x sub n plus y sub n squared plus h squared over 2, let me just put the bracket there because I know I'm going to need it, times the quantity 2t sub n minus quantity t sub n plus x sub n squared minus y sub n plus 2y sub n times t sub n squared minus x sub n plus y sub n squared. Yes. And then my final bracket. Wow. That is crazy. It's a huge monster, right? From what you see there. So this is how, this will be a Taylor method of order 2. And do I actually have any values that I inputted for it? Oh, I forgot to put my initial conditions. Sorry. My initial conditions are x sub 0 is equal to 3, y sub 0 is equal to 2. Now it's complete. It's so complete that I'm going to put a box around it. this is my answer. And do I have any system for it? I don't think I did. This is where a Excel or a computer would come in handy. I don't think I wanted to actually approximate a solution using this. This would just take me too long, All right, so we're gonna stop there with this one. And we'll pick up again, one more thing before we go to Runge-Kutta. And we're gonna talk about how to change a nth order equation to a system of equations and then be able to use this method, either Euler's method or Taylor method of order 2, 3, 4, or 5 to be able to find a solution to a nth order differential equation. All right, bye.